Center.
All right, we're gonna go ahead and get started. We've lost some people. It seems like this is less full than it has been. Fun. So quick announcement, I put in an IT ticket about the technology not working downstairs. What that means is until they can come look at it, I would like to be able to continue recording. And I also checked and there's nobody meeting in this room Wednesdays and Fridays. So let's try to meet in here tomorrow at the very least. And I'm hoping that by next Wednesday, things will be at a point where we can meet in the lab and record in the lab. But until then, we will be meeting in here every day, just so that I can continue to record class so that you can access it at a later time and date. I also wrote and revealed a first homework. Everybody see that on Canvas? So there's a reasonable amount to that homework because, as a couple of people have mentioned, there's a pretty steep learning curve at the start of this class. You're doing some thinking and seeing some things that you haven't really seen before. So as part of that, there are going to be a lot of practice problems to get you to the point where I would be comfortable giving you an exam on this material. So I think there were 24 questions in that first homework, so that's quite a bit. But start early. It isn't due until next Wednesday. So that if you evenly space them out, that's about 4 problems per day. I felt okay with that, but just try not to procrastinate it until the last day. That last day will really suck if you do that. So last time we introduced DFAs and we were talking about some of the, we started getting to practice putting together some DFAs based on some languages. So we looked at the language now of all strings except those containing the substring 001 in the binary alphabet. Did everyone get a chance to come up with some kind of solution to this? Have we thought about it since yesterday? What did people come up with? Maybe it's easier if someone comes up and draws their solution on the board. Does someone want to do that? You can even pick a color. Sure, Hunter. As long as it stays within the shaded region here, then it can be seen by the camera, whatever is light. Yeah. That looks right to me. Is this the same or very similar to what other people got? About the same? As mentioned before, there's no one correct answer with any particular DFA or with any particular language. There are many different DFAs that will represent the same language. So this is not the only solution, but it happens to be exactly the solution that I came up with. So it's good. One thing to note is that you can also think about each state, not just by its name, Q0, Q1, Q2, or Q3. You can think about it by how much of the target question has it answered, and you can use that to label states kind of intuitively. So if we look at Hunter's diagram, what this state represents is basically nothing. If you're thinking about it in terms of how much of the substring 001 have we identified so far by being in this state, because we want to not accept anything that has that 001. So these states represent, we haven't seen 001, and as soon as we see 001, then we want to transition to this trap state. So this represents that we've seen nothing of the substring 001. This represents that we've seen the first zero of the substring 001. This says that we've seen the first zero and the second zero of that substring. And then this state represents that we've seen the entire substring. So we want to reject the input. Does that make intuitive sense? Any questions about the construction of this? The logic that leads you to the construction of this? I think that by thinking about that in terms of how many of these symbols have we seen so far, that helps you to figure out how many states there are going to be, as well as what the transitions look like. If you've seen a zero so far in this substring, and you see another zero, you want to transition to the state that represents that you've seen the first two zeros. And that makes this make a little bit more intuitive sense than just states and digit transitions, or however else you might see it. There is intuition buried in there, and try to design from that intuition, and that will help you get to the final answer faster. All right. Here is the copy pasted solution. So we're going to talk about the kinds of languages that these diagrams represent. If you can draw a DFA for a particular language, then that language is what we are going to call a regular language. One thing to note, if you draw some kind of finite automaton, whether that be a DFA or the NFA that we're going to get to later today, then it accepts some language. And if we think about the set of all language that any DFA could accept, what you can draw a DFA to represent, because there are some languages that cannot be represented by a DFA. We'll come upon those and learn how to deal with that in a bit. But there is a class of languages that you can construct a DFA for. We'll call this a family of languages. And I already spoiled the answer to this question, but so the answer is yes. The family of languages accepted by a DFA is limited, but what do we think that limiting factor is? What keeps us from being able to represent a language with a DFA? Or what is the limitation of what a DFA can represent? Take a little bit and think about that, because it's not a really apparent answer. I don't expect anyone to have an answer for that in 5 seconds. Yeah, so thinking about if I give you a language and say, build a DFA that represents this language, that's going to be true for some languages and not true for other languages. So what is the limiting factor in a language that means that we can or cannot construct a DFA for that language? What kinds of languages could we not construct a DFA for? And then what is the limiting factor between what separates languages we can represent a DFA with and languages we can't use a DFA to represent?
Are there any languages that have like contradictory rules, but where they don't together? Because they have like
Interesting idea. What do you mean?
I guess 2 sets of grammars that would not work together. I'm not sure what I'm saying.
I think I understand what you're saying. In general, no, you have a single grammar that represents a language, but as we're going to see when we come up with grammar rules to represent regular languages, we have to place restrictions on how those grammars are constructed. And it's going to be a very similar idea of if you adhere to those restrictions, you get a regular language. If you relax that restriction, then you can get some languages that are not regular.
It's like a really niche case, but like intuition wise, I'm not using my whole brain. Stuff like maybe like quantum language, like qubits or something.
Okay.
States can ever change as you do it, and stuff that are not well defined, but that's just a guess.
Yeah, that's a really good guess. And the answer to that would be that we're going to talk about that when we peel off a few more layers and talk about some languages that are less and less and less restricted. Then you start getting into that. What I'm targeting with this is something that's a little bit more concrete, but we will get to that later in the course because that is an important distinction.
Languages that aren't deterministic, so in one, like, I guess one state in the DFA would have the same output going to different places.
It actually turns out that that is also regular, and we can convert that concept into something that is a DFA. And we'll talk about that over the next few days. So that's a really good idea, good thinking. It turns out that that distinction has to do with how much memory we need in order to represent and construct strings in that language. If we have a finite amount of memory and we say for any string in that language, we need this finite amount of memory, or we can use this finite amount of memory to construct any of those strings, then it is regular. As soon as you need something like a stack with infinite memory to be able to, as the strings get longer and longer or more and more complex, you start needing more and more memory to represent them, then you start getting into languages that are not regular. And that's kind of a cool distinction. I didn't really expect that people would come up with that, but it's worth thinking about when you're starting to think about different classes of languages and what those restrictions actually are and mean. So we will just for now define any language that a DFA can accept as this concept of regular. And we'll spend the next week or so just talking about regular languages and all of the different ways to represent regular languages, what they mean, what they can represent, and some of the applications of regular languages. Like we'll talk about regular expressions. Have people heard of the concept of regular expressions? Completely identical. Any regular expression that you can construct is a regular language, and vice versa. If you have a regular language, you can construct a regular expression for it. We'll talk about that in a couple of days. So now we ask the question, how can we prove that a language is regular? If I asked you to prove that a particular language is regular, how could you do that? Yeah, exactly. It's not some long convoluted proof or proof method that you might see in a math class. If you can construct a state machine that adheres to the DFA rules of construction, then you have proven that that language is regular. We'll talk later about regular expressions. You can also construct a regular expression. We'll talk later about regular grammars. You can construct a regular grammar. If you do any one of those things, you've proven that that language is regular. So draw a DFA. So because this is the actual proof mechanism for this, it's worth thinking about and getting some practice with this so that you have a tool set for building DFAs. So we'll use this to segue into example problem 3. So we're going to start using some of this more formal language for representing languages, because I think it's good to be able to read this. So this says the language L, which again, the characters for this, the alphabet is just A and B. They're going to be A and A bookending some string W, where W is the closure of that, which means that there are 0 or more repetitions of any combination of A and B. So this is just identifying the language of all strings in AB that start and end with A. So take a few minutes, talk to your neighbor, and see if you can construct a DFA.
I have a question.
Yeah.
My work says, with the asterisk went to,
This is closure, the concept of closure, which basically just means 0 or more repetitions. So this is saying this W is a string that could be, since this is 0 or more, it could be the empty string, but it could also be A, B, AB, BA, AA, BB, AAA, AAB, any possible string of 0 or more repetitions of the characters A and B.
page. I don't think that's it. That's a great. Right.
You think they have an answer? A few people, I'll give you a little bit longer. If you're still working, make sure you're talking to your neighbor. Putting your brains together may end up with a faster solution.
I just like start to be. Just kind of noting this. Just trying to say. Always so you want to just like space and here and that's just get pretty fast. And then I guess other way to get to the city, so you know, if it's the last one, it's me. So that because the last one you can vote there. And then you're gonna be here, you're just gonna say this. So basically, just a way of panic. So it just brings to a lot of this. It's like it puts her in. It has to finish and then sort of stay.
So if you're still working and struggling, I have kind of an outline here that might help you. Instead of labeling the states with Q0, Q1, you can erase and label them after you've finished. Here's kind of the intuitive ideas outlining what the states in this DFA might represent intuitively. We want some kind of trap state if it starts with a B, because there's no way for it to start and end with an A if it starts with a B. If it does start with an A, we need some logic that's going to connect starts with an A with ends with an A. And you may or may not need some additional states in there to handle that. There are solutions with both. These are the only states that you technically need, but there are some solutions with more. So just connect the dots from here and try to figure out what did those transitions look like to get an answer. How do we finish this off? What last connections do I need to make?
Well, for one, you can put a loop at starts with B to just stay there no matter what.
Sure. Finishes off the trap state. How do we connect these states? Yeah,
Starts with an A, it's an A, goes to ends with an A, and with the A has a B, it goes back to starts with an A.
if it starts with an A and we get a B, we need somewhere to put that. What should we do with this on a B?
Just stay there.
Stay there? And then we also need ends with an A and has an A. What should we do?
Stays there.
Stay there? That gives us that total function we were talking about last time, where we make sure that at every state, we have a transition for every possible alphabet symbol. That finishes it off. So note that this ends with an A, that's necessarily, you don't just end up there if it ends with an A, it ends with an A so far in the string. So this really would be better worded as the current last symbol that I have seen is an A. And that makes sense here that we need to see at least two A's. A single A does start and end with an A, but is not part of this technical definition. So we do need to see two A's in order to get to a final state. Questions about the construction of this DFA? Or why it works, why it represents the language that is up there? Yeah.
Quick question, just for like homework and further on going on, it's not gonna be something like, I've heard like within chemistry where you have to do it within a certain amount of nodes or
There
steps.
only if it is specified in the problem.
Okay,
And we will be talking about some algorithms to reduce the number of states of DFAs, to minimize the number of states of DFAs, et cetera. So you will have tools to be able to, if a problem says that, it's probably asking you to implement that particular algorithm. But I will introduce that algorithm as part of it. I think there are a couple homework problems that have you doing that. But if it's not said, then I don't care. Other questions? All right. There's the solution we just described for future reference. One more problem. So we're going to take the same language and we want to be able to show that that language repeated is also regular. So what this means, elsewhere just says that we're going to have a repeat of that language. So we had before A, W, A for some string W. Now we're going to have A, W, A, W, A. But note that this is W1 and W2 now because they can be different. So this W would not necessarily have to map to that W, but it represents still that there could be any closure of A and B at either of these positions in the DFA.
Yeah, I'll specify. Yeah.
What do we think is a good starting point for this problem?
Q0.
Yeah, that's a very good starting point.
But we didn't have.
Can we start with the DFA that we drew for the last problem?
Pretty much. Mostly, I think.
Let's start intuitively there. Start with that DFA and figure out what changes need to be made to that DFA. Hint, it's only one. And then how do you extend that DFA to get a solution? I take that back. It's two changes. You think they have an answer? I'll let people work for a little bit longer. Again, talk to your neighbor if you're stuck.
Dictionary. Quantum is congeniality.
So here are the two changes. Ish. So what, before this used to be a final state, right? We had B going back here, that's gonna stay. Before, we had this A looping and staying here. That may need to change. Because if we see an A from this state, it's gonna become the first A from the second repetition of this language. The other one is this used to be a final state, and this is definitely not a final state anymore. We've reached the end of part one of this, but we need to start part two before and finish part two before we can accept the string. So this is no longer a final state. I would argue that we are going to need more states.
It's gonna be pretty much the same thing repeated.
Yeah, we're gonna take this concept and put it over here to be able to say we need to be able to represent that same idea. So we are going to move on to a Q4 on an A. That represents this transition. We will loop here on a B, just like we did here, and we'll move on to a Q5 on an A, and we'll go back to Q4 on a B. Should I make Q5 a final state? Yes, I should. And that'll solve the problem. Aside from needing to loop this on an A. So DFAs can get a little bit more complicated as we start doing more complicated things, but we notice how you can kind of discretize sections of this representing parts of your string. We have the first part and the second part that allows you to construct that. Yeah.
So the W has to be a or B.
It could be nothing, it could be an A or a B, it could be any amount of A's or B's. It's the star closure of AB. So that represents. If we continue that sequence on forever, that represents the concept of AB star. So yeah, the star in this case just means zero or more repetitions of any element in the set. So you can continue to pick and choose any number of times. This represents all of the ways you could choose one element, all the ways you could choose two elements, and you will see that there are 2 of these, 4 of these, there'd be 8 of size 3, 16 of size 4, 32 of size 5, and there's no upper limit on that. You could have a billion characters in between representing W1, and that would be perfectly fine. But note that after you parse that length billion string, if it adhered to this format, this DFA with just 6 states would be able to accept that string as part of this language. The length of that string does not depend on the number of states you have here, yeah.
So does this potential length of strings not have anything to do with that issue of like infinite memory not being accepted by a DFA? Because technically you could have.
It's on the input. It has nothing to do with the construction of this or needing that memory as you're calculating it. You can still parse a billion strings with just this much memory. The ability to design this structure, which is very limited. You have, this is the limit that you can parse an infinitely long string. It still has to be finite, but there's no upper bound on that level of finite.
Can I just repeat what you just said, because I don't want to be lost in the sauce?
Yeah.
So the input could be infinite, but this diagram that we do needs to be finite. Is that what you're
Yes.
saying?
Yeah, and we don't need to store. The infinite comes from the amount of memory that's required as you're using this diagram. So if you think about things like, what do you need to remember as you parse a string that's a billion characters long? What do you need to know? You need zero memory for that. You're working with the current character, and then, I mean, you need to know which state you're in. But other than that, you don't, the fact that it's really, really, really long does not scale the required memory at all. Memory is very small and very finite, even though the input is unbounded.
So I'm not sure how to phrase the question quite right, but how do we know if the last A in the string came from W2 or if it came from? Yeah, not sure with that.
Yeah,
Well, I mean, there could be a part of the string, the W2, and there could be A that's separate and after.
yeah. So basically, we don't necessarily need to know. This will be the first A scene, the second A scene, the third A scene, and the fourth A scene, because we never go backwards in this diagram on an A. We only ever move forwards. So whatever happens, we're going to be in this accepting state after we've seen four A's, and then cycling between Q4 and Q5. Since there's no way to go backwards from Q4 to Q3, if the last thing we've seen was a B, we'll be in Q4. If the last thing we've seen is an A, we'll be in Q5 and accepting. So it's just a matter of cycling between Q4 and Q5 until we see the last character. And the question is the last character a B, in which case we'll terminate here? Is the last character A, in which case we'll terminate here and accept the string?
Okay, I think that makes.
Because there's no way to go backwards. So this is just looking at the first A, second A, third A, and fourth A in the string as a whole.
You're saying it doesn't matter where in the string the two A's are, as long as there are two A's at one point, then it ends with A, it begins with A. It doesn't matter where those are in that string.
Right. So like if we have a really, really, really long string where we have A, B, B, A, we'll see that the first A will get us to Q2. We start in Q0. We'll get to Q2. Then we will stay in Q2. We'll move to Q3 on that A. We'll move to Q4 on that A. And then we'll stay in Q4 until we see this A, and then this is the fourth A in the string, A. This will put us to Q5, the accepting state, and if the string ended here, we would accept it, because it has four A's. And so then this becomes W1, and this becomes W2. But we're not done. So we can read the next A, and if the string were to end here, we would still have transition from Q5 to Q5. But now W2 is BBA. And this last A now represents the last A in that. And then we continue reading, and then we have this B, and if it terminated there, we would have transitioned back from Q5 to Q4, and we're in a non-accepting state when we finish this string. So if this were the end, we would reject the string because it doesn't end in an A. We continue the process, and here we read this A, and we would be back in Q5. W2 now is even longer, but it ends right there. but it still ends in an A, we would be in Q5, we would accept.
And just to be clear, which part of this is memory? Is it the Q nodes or the whole thing?
The memory is the amount that you're storing as you're parsing this. So basically, if you can imagine an extra box here with additional memory that you need. One restriction to regular languages is it can't handle things like, I'll give you the classic example. Something we've already seen in the class, A to the N, B to the N. We need memory to figure out how many A's we've seen to be able to take them away when we start counting B's. If you imagine trying to design a DFA for this, we would need an infinite number of states to be able to represent an infinite, potentially close to infinite number of A's. How do we know how many A's we need to count back, how many B's we need to count backwards to figure out if there are an equal number, if we don't know how many there were to begin with? That's why we need this memory right here to eventually store how many A's did we see. So that we know how many B's we need to identify before we can accept or reject if there were an equal number of A's and B's. We get to this once we start talking about the restrictions on regular languages, but that's the kind of memory that we're talking about. As we parse the string, we need to store something to be able to determine yes or no, we accept or reject. We don't need that in this case.
So are W1 and W2 just different sections of the same input string?
Yeah, they're just between W1 is everything between the first A and the second A, and W2 is everything between the third A and the last. If we wanted to put a name to what those represent.
Okay, so this is sort of like, I'm not sure if this even matters or not at all, but let's say like W1 ended up being BA. So like that second A is that just something you would never do?
Yeah, according to this diagram, it's not something that could ever be done, because it is something that you could technically state that that is the case, but how we've constructed this DFA, at least if we're referring to the DFA, then the difference between going to Q2 and going to Q3, there cannot be an A and staying in this part of the DFA. So because of that, this W1, according to this DFA, would just be everything between the first A and the second A. Some number of B's, could be 0, could be a billion.
Oh.
Very abstract, I know. Very abstract, yeah.
So in this case, do W1 and W2 almost have wildcards, where it's just saying it could be anything in here?
Yeah, that's kind of, if you've seen the wildcard character, it's always that star. It's the same in a closure idea of being 0 or more, it's a wildcard. It could be 0 of these, it could be 10 of these, it could be, but it will still represent some number, 0 or more of them. So that's actually a good idea and a good way to tie these concepts together. It's very similar to the wildcard.
So I'm looking for a really short answer on this one. In the memory part, how many A's, we just have to store how many A's, we don't have to, like, the number of A's, not the entire string.
Yeah, and there may be some where you do need to store the entire string, but the idea is we actually need a stack in order to be able to answer the question, is a string in A to the N B? Basically, for every A we see, we're gonna be pushing it onto a stack, and then for every B that we see, we're gonna be popping it off the stack. And if we can design one of these and kind of keep a stack along with these nodes, then that's the memory required. This is not regular. In fact, it is what the next class of language we will talk about context free. But we'll get into that once we get there. All right, excellent questions. How are we feeling about this at the moment? So just like, give me the usual show of thumbs. Does this make, do you feel like this makes sense? Kind of makes sense, need to see it some more in practice, it's some more help. It seems like it makes some sense, which is good. There's definitely a lot here, it's very theoretical, it's very abstract, but this gets us to the diagram that we need to be able to answer whether or not it's in this language. And I'll end class with this really interesting theoretical idea where All right, so we've seen that we had some language. And then we're able to construct a DFA for L squared, that language repeated. Is that always going to be the case? If we have some regular language L, is that language repeated always going to be regular? The answer is yes. And it does not matter how many times it's repeated. L cubed will be regular. L to the fourth will be regular. L to the fifth will be regular.
So as long as L is possible, then that's what yeah.
Right, yeah, as long as L is regular. If L is not regular, we make no claims about L squared or L cubed. In fact, they're not going to be regular. But yeah, you can map directly. If L is regular, then so is L squared, L cubed, L to the fourth, etc. Awesome. Well, I think I don't want to dive into exactly, non-determinism is a longer talk than 2 minutes. So we will start that talk tomorrow. Sit on this, start some homework. Yeah, and come to class, prepare with questions tomorrow for this. Remember, we're meeting in here tomorrow, not down in the lab.
Yeah, so that would just be nothing, yeah. Oh, no. No, not like this, I'm not waiting, guys. Well, you're DC? Yeah. Oh, they have been there.